All right, let's look at this first one. So we are looking for the cubed root, meaning we want to look for things that group up 3 times. All right. You do not have to multiply the 40 and the 54. You can just factor those individually and then look for things that group amongst all of them. So if you factor them individually here, we're going to take the 40, and I would do 2 and 20, 2 and 10, 2 and 5. Then we can take the 54. Same thing here. All right, and once we have it completely factored, we're going to look for things that group up in groups of 3. All right, so groups of 3 will come out. So we have 3 of these 2's right here, which means that a 2 is going to come out. We have 3 of these 3's, which means a 3 is going to come out. Those are the only things that can come out. So inside the root, we have this 5 right here, and we have this 2 right here. All right. And so remember, everything that's on the outside multiplies together. 2 times 3 gives us that 6. 5 times 2 gives us that 10. And don't forget that you want to put the index there. So your answer is 6 cubed root of 10. So for 20, we are looking for the 4th root, meaning it has to be in groups of 4 in order to take it out. So again, we're going to do the same thing with our factor tree here. And this is actually just one more. Lots of 2's, all right? But they have to be in groups of 4. So we are going to look at groups of 4. So we have 1, 2, 3, 4 2's right there. All right, so we can take a 2 out. All right, we have 1, 2, 3, 4 2's right there. Another 2 can come out. But the ones that we have left, we only have 1, 2, 3 left. So that's not enough to group, which means it has to stay inside the root. So we have 2, 2, and 2 inside the root individually. And then we are going to, of course, multiply the 2 and the 2. That gives us that 4. 2 times 2 times 2 gives us the 8. Don't forget to put your index. So we have 4, 4th root of 8. When you look at this one right here, the index is 2. You don't have to write it, but that you do have to know that's how you're pairing it up. And once again, you can group them. So we have 2 and 2 there. We have an A and we have a B. The 5 is already prime, and we have a B. Those are all my factors of those 2. We have one group of 2 that's going to come out. We actually also have B's that can come out. Those B's group up. So a B can come out. Those are the only things that can come out. On the inside, we have this A and this 5 that cannot group. And so that is your answer. So the first thing you see on this page is the quotient property. For every x greater than or equal to 0 and y greater than 0, if you have a fraction under the radical, you can split it up. So basically what they're telling here is you can either reduce the fraction first, or you can take the radicals individually, whatever works best. But when you are dividing them, you are strictly dividing the numbers on the inside. So just like with multiplication, if with multiplication you multiply the outside to the outside and the inside to the inside, with division, you would divide outside to outside, inside to inside. You cannot divide from the outside of a radical to the inside of the radical. The other thing you want to notice with the radicals is you have to have the same index, which I will always give you at this point, but you do have to have the same index in order to divide. All right, so let's look at this first example that they give us. The first example is the square root of 40 divided by the square root of 5. And so typically when you have these, it's easiest just to write them as a fraction. That's the same thing as the square root of 40 over 5. All right? Which you can easily see reduces. How can I reduce 40 over 5? Yeah, so it's going to be the square root of 8. So then once we have done the division, we want to see if we can simplify the root. And so to do that, we're going to do what we just did on bell work. We're going to say 2 times 4, 2 times 2. My index is 2, so anything that groups up in 2s is going to come out. Anything that doesn't group up is going to stay in. And so 2 square root of 2 would be my answer here of the square root of 40 divided by the square root of 5. So that's one way you can see it. You can see it written out long ways with division. The next example shows it to you this way. Square root of 15 over the square root of 12. Remember, you can divide inside to inside. So just like any fraction, you can look to see if this will reduce. Does 15 and 12 reduce? What goes into both 15 and 12? Yeah, 3 goes into 15 and 12, right? So you can think of it this way as well. That's the same thing, which means you can just divide each one of those by 3. All right, so 15 divided by 3 gives me what? The square root of 5. 12 divided by 3 gives me the square root of 4. Can either of those reduce? Square root of 4 can. What is the square root of 4? 2. And so I can rewrite this to be square root of 5 does not reduce at all, but the square root of 4 is just 2. And that is my answer, the square root of 5 over 2. And I would leave it just like that. So if you have a perfect radical, just take the square root. All right, so if you have a perfect root, just take it. Square root of 4 is just 2. It says fractions with radicals in the denominator or radicals with fractions in the radicand are not considered to be simplified. What they mean by that is this fraction here, square root of 5 over square root of 7, or the square root of 5/7 is not considered simple. So having a radical in the denominator, whether it's looks like this or whether it looks like this, is not considered simplified. It would be like giving me 2/4 as an answer. It is not considered simplified. So we use what's called the quotient property. It's actually called rationalizing the denominator. Rationalizing the denominator. All we're doing is getting the radical out of the denominator. The reason we do this, it is not considered a simplified number if you still have a radical in the denominator. And so in most cases, especially on like standardized tests, you could get an answer and not recognize it because they have rationalized the denominator and you did not. All right? So we're going to do this process when the denominator does not equal just a number without the radical, then you have to rationalize it. So let's look at these examples. The first one they give us here is the square root of 5 over the square root of 7. We really can't simplify this anymore with the numbers. The square root of 5 over 7 does not reduce, and the square root of 5 and the square root of 7 are as simple as they get. And so normally you would think, well, that's as simple as we can do it. But because you still have that root in the denominator, you need to get rid of it. And so the way you get rid of it is you simply multiply the top and bottom by the root that you're trying to get rid of. So let's see how this helps us. If we take this square root of 5 and square root of 7, and we multiply the top and the bottom by the square root of 7, first of all, with fractions, if I multiply the top and bottom by the same number, am I changing the fraction? No, because the square root of 7 over the square root of 7 is just 1. So I have basically multiplied that fraction by 1, right? On the top, what happens when I multiply? Well, I just multiply the insides. 5 times 7 gives me the square root of 35, all right? What about the bottom? I am multiplying a square root of 7 times a square root of 7. What does that always end up being? Just 7. Remember when you multiply a radical by itself, you get rid of the radical. Or when you multiply a square root by itself, rather, you get rid of it. Because this is basically the square root of 49, which actually has a perfect root, which is 7. You don't even have to do this step. You can actually go straight to here. This is considered simplified. All right? This is not simplified because you still have that square root in the denominator. And so in order to get rid of the root, you are going to multiply it by itself. Now, we're not going to do any higher roots when we get into Algebra 2, we'll do higher roots as well. But this is a square root. If this was a cubed root, you actually have to multiply it twice. You have to multiply it by as many times as you have a root. But right now we're going to do square roots. Let's look at the next one. Simplify the square root of 3 over the square root of 6. Now, if we write this one out, square root of 3 over the square root of 6, we can actually reduce it. 3 over 6 reduces to what? 1 over 2, right? Square root of 1 over the square root of 2. What is the square root of 1? That's just 1. So we actually end up with something that looks like that. But this is not in simplest form because I still have the square root of 2 down there. So once again, I am going to take that 2 and I am going to multiply the top and the bottom by the square root of 2. And so when I do that, I am going to get the square root of 2 on top and I am going to get just 2 on bottom. Now remember, you can only reduce within, inside to inside or outside to outside. So part of you is going to want to reduce that, right? Part of you is going to be like, oh, well, 2 over 2. One of those is inside a root. One of them is outside the root. This is as simple as you can get it. This is your answer. All right, so for this one, I have the square root of 2 over the square root of 75. Is this as simple as I can make it right now? No, the 2 can't reduce, but what about that 75? So the first thing I want to do is simplify. I don't want to multiply by the 75 right now because I'm going to have something that's not as simple as it could be. Square root of 2 is as simple as it gets, but this guy can reduce, right? 3 times 25, 5 times 5. Everybody see that? All right. So I can actually take something out here. The 5 can come out, right? And the 3 will stay in. Now, both of my radicals are simplified, but I need to get rid of that square root on the bottom. So in this case, I don't have to worry about the 5. I just have to worry about the square root of 3. So if I am rationalizing this, I'm only multiplying by the radical. I'm only going to multiply by the square root of 3. You do not need to multiply by the 5. You're making extra work. You'll have to reduce again if you do that. All right? So I only have to worry about the square root of 3. On the top, I'm just going to multiply the 2 times the 3, square root of 6. On the bottom, I have this 5 out here, times, and what happens here? What does that whole thing become? Which is just 3, right? So remember, I multiplied it by itself, and then I'm going to simplify one more step. The square root of 6 stays the same. 5 times 3 gives me a 15 on the bottom. This is my answer. All right, so we have 25 square root of 3, 9 square root of 15. All right, so I am going to look at two things here. I'm going to look at my outside numbers. Can 25 reduce with 9? It cannot. All right, 25 cannot reduce with 9. What about 3 and 15, inside to inside? Can those reduce? Yes. What goes into both of those? So for the insides here, I'm going to do divided by 3, divided by 3. My 25 on the top stays the same. 3 divided by 3 gives me the square root of 1. On the bottom, my 9 stays the same. 15 divided by 3 gives me the square root of 5. All right, the square root of 5. Now, I have this perfect square root here, right? 1 is a perfect root. So on the top, I end up with 25 times 1. Right, so just 25. 9 square root of 5. All right. But I still have a root in my denominator. So I need to do the rationalizing. I need to multiply the top and the bottom by the square root of 5. All right. On the top, I have 25 square root of 5. And on the bottom, I have 9 times 5. Do you think I can reduce anything right now? Yeah, this 5 is now on the outside, right? He's no longer under a root. So before you multiply these, you're going to get numbers you can reduce because this 5 will reduce with this 25. It's just multiplication. You can reduce it. And so before I do anything, I'm actually going to go ahead and reduce this one. 1 and 5. And so now on the top I have 5 square root of 5. And on the bottom I have 9. Now if you had not done that, you would have 25 square root of 5 over 45. And hopefully you would see that you can reduce both of those by 5, right? So anytime you have stuff on the outside that can reduce them. Insides you can reduce them. All right, so your final answer here is going to be 5 square root of 5 over 9. 49. Write the radical in fraction form. So they want you to put it, if it's spread out with a division symbol, put it on top of each other. It will be easier to see that you can reduce. Simplify the numerator and denominator as much as possible. If you have numbers on the outside, by the way, you reduce those as much as possible too. If you have a radical left in the denominator, multiply it by the number that gets rid of it, all right, to make it a perfect power, and simplify the numerator and the denominator. So even after you rationalize, you may then be able to reduce again. You may be able to reduce again with your outside numbers, all right? So let's try some of these. So we start out with 3 square root of 5 over square root of 15. All right, we look at the outsides, it's just 3 and 1. On the insides, though, we can reduce by 5. So we can reduce both of those by 5. We get 3 square root of 1 over the square root of 3, which, of course, that just ends up being 3 over the square root of 3. This is not simplified yet, though. We want to multiply the top and the bottom by the square root of 3. So on the top, we get 3 square root of 3, and on the bottom, this just becomes 3. And then we can reduce the 3 over the 3 becomes 1 over 1, which just gives us the square root of 3.